In Unit 10 fields, we'll be covering both electric fields and gravitational fields. However, in order to fit in better with the SL units that we'll be covering, we'll do electric fields first, and then later on in the course we'll come back and look at gravitational fields. So before we get stuck into electric fields, we're going to do a quick review, and this quick review, basically we just need to go over some of the key things about electric fields in order to make sure we're all at the same starting point and clear on some of the terms that we'll be using. If you need more detail about some of this stuff, you can always refer to the subtopic 5.1 electric fields, where these concepts are explained in much more detail. But we'll just jot them down here so that we've got them in the forefront of our mind. The first thing is that there are two types of charge, and those two types of charge we know quite well. The two terms that we'll use there are negative and positive. And just to provide a little bit more detail there, if we're talking a negative charge, what we mean is that there is an excess of electrons on the object that we're dealing with. And if we're dealing with a positive charge, we're dealing with a deficit of electrons, or a loss of electrons. So those two terms are fundamental to looking at electric fields. If we then have two charges, or two charged objects, we would have an electrostatic force between them. And that electrostatic force depends on a few different quantities. Again, if you want the more detail about it, go to subtopic 5.1. And just very briefly again though, just to make sure that we're clear, that force will be attractive when charges are opposite. So if you have two charges, one that's positive and one that's negative, then you'll have an attractive force between them. And it will be repulsive when the charges are the same. The size of that force is given by Coulomb's law, and that we can summarize in equation form as kq1 q2 on d squared. Next thing, if we're looking at electric charges, it's important to note that all electric charges have an electric field around them. And we're not necessarily just talking about point charges here, we're talking about any charge on any shaped object, and we'll develop that a little bit further throughout this unit. And a couple of key things about those electric fields. If we're dealing with an electric field, we're really looking at the force on a small positive test charge. If it's placed at that point. The other key things to note here as well, the electric field is represented by field lines, and in this case we'll call them electric field lines. As I mentioned, we'll be looking at gravitational fields, and we talk about gravitational field lines there. So for electric field lines, a couple of things that you need to remember. First is that the arrows show the direction of force, and the direction of the field. And the second thing is the spacing of the field lines. And the spacing shows the electric field strength. And the electric field strength can be summarized in an equation, and that equation is E being the electric field strength, is equal to F on Q. And just to remind you, electric field strength is measured in newtons per coulomb. As you can see in the equation, F divided by Q. Last thing we need to remember about this particular, or going back to unit subtopic 5.1, is about potential difference. And this is going to be a fairly key point to understand looking through this fields unit. Potential difference is a measure of the energy when moving a charge through a field. So if we have a charge in a field and we move it through the field, we're looking at the amount of energy transfer that's occurring by causing the charge, or by applying a force to the charge to move it through the field. In that scenario, the potential difference that we would be looking at would be expressed using the term V. Sometimes you might see it as delta V for potential difference. So either of those two, just be aware that there is a couple of different representations depending on the circumstance. And the equation is W on Q, and potential difference is measured in volts. That has the symbol V as well. 1 volt is the same as a joule per coulomb. So just hopefully you can recall that. So there's a very quick overview of the key concepts that you need to have in the back of your mind for this first part of the 10 point, the unit 10. For gravitational fields, there'll be some other key ideas that we'll need to come back to, but these are the ones to keep in mind for electric fields.